Okay, in the last class we discussed about ionization enthalpy, and we saw that ionization enthalpy increases from left to right in a period and decreases from top to bottom, and so does electron affinity, EA. That also increases from left to right and decreases from top to bottom. Ionization enthalpy follows a trend which is opposite to metallicity, or metallic behavior. So metallic behavior decreases from left to right and increases from top to bottom, and non-metallic character increases from left to right and decreases from top to bottom. So the most metallic elements are found on the left-hand side in the bottom, and the most non-metallic elements are found on the top towards the right. And that's why you have more non-metallic things happening on the right side, more metallic things happening here, and the trends are increasing, non-metallic trends are increasing this way. That is why, since metallic oxides behave as bases, so the basic character decreases left to right, acidic character increases left to right. Basic character increases from top to bottom, and basic character decreases from top to bottom. Now, there are multiple definitions of acids and bases. One of the simple definitions is the Arrhenius, I think is the Arrhenius definition, which tells anything that produces H plus is an acid, and anything that consumes H plus is a base. So H plus producers, I think this is the Arrhenius, doesn't matter. And these are H plus consumers. Bronsted concept is, this is OH minus consumers and OH minus producers. Lewis concept is electron acceptor and electron donor. This is the most advanced form, this is the most latest form, latest definition of an acid, and this will be able to explain most acidic and basic behavior anywhere in nature. Some will be explained by this, some will be explained by this, but almost all will be explained by this nature. So anything is an electron acceptor is a Lewis acid. So Lewis acid is an electron acceptor. So I remember it by this. So a Lewis acid is an electron acceptor, so both A's. And the other, the Lewis base, is an electron donor. Now, if this is true, or if this is the definition, we'll be able to understand there are certain compounds that might not have H plus or OH minus, but they can still behave as an acid or a base, like NH3. What do you think NH3 behaves like? Will it behave like an acid or a base? Courtney says acid. Guess, I mean, there could be only acid or a base, but just, acid. Okay, why?
It's a non-metal.
Okay. It's a non-metal, and that is why since non-metallic oxides have behaved like acids, you are thinking non-metallic hydrides will also behave as acids. But think about, so can everyone see these? What are these two that I have like noted here? What are these things? Take a guess.
Isn't the state of nitrogen?
No, yeah, it is nitrogen, but what is this, these two dots? What are they signifying?
Is it electrons?
They're electrons.
So what we're looking at there is 2 electrons to 3 as a positive H plus. Correct?
Yes, so
Which make it
nitrogen has, yes,
Those are like the 2 electrons that didn't pair with any of the hydrogens.
yes, those are the lone pair of electrons that did not pair with something else. So we are getting into bonding now, okay? Now, I want you guys to see like how this all things are connected. Like that's why I'm like jumping from one concept to another, because all these things are very much related. Now, nitrogen, how many electrons did nitrogen have in the outermost shell? What's the atomic number for nitrogen? 7. So what's the electronic configuration? Look in the periodic table quickly. 5. 7, so 2, 5, right? So it's in the 15th group, 5 electrons in the outermost shell. How many more electrons are needed for nitrogen to be stable? What's that rule that governs most behaviors? The octet rule, right? So it already has 5, so it needs 3. So it is bonding with hydrogen to share 3 electrons. Now we are getting into bonding. So you already know about bonding. Bonding happens because the elements need stability. So there are different types of bonding that we'll be looking into. The most common would be covalent. Then we'll have ionic. Then we'll have metallic bonding. Covalent and ionic you must have heard before. So covalent, in which the electron pair is shared between the two parties that are involved in the bonding. So bonding is basically some kind of electron sharing or donating or accepting for stability. And this is basically governed by the octet. Okay? So now the question is, what are the things that will form, let's just imagine, covalent versus ionic. So let's just think what covalent and ionic is, and then we'll be able to figure out which things will be forming a covalent bond and which things will be forming an ionic. A covalent is in which the electron pair is shared. The ionic is in which the electrons are donated or accepted. They're not shared. There's a complete transfer. Now, based on electron affinity, so we saw ionization enthalpy, we saw electron affinity, and there was another thing which is electronegativity. So electronegativity is something you can think of it as analogous to the non-metallic behavior. So things which are very electronegative, they will be more non-metallic. So what is electronegativity? Electronegativity is the tendency to pull the shared pair of electrons. And that is why we hold the discussion of electronegativity till we get to a place where we can actually see that bonded. Because electron affinity is the tendency of an element to attract the bonded pair of electrons towards itself. So whenever there is a bond between, say, A and B, whichever has more electronegative behavior will pull the electrons. For example, if there is a bond forming between H and F. Now, F in nature, F is more electronegative. It's just the nature of fluorine. Okay, the nature of non-metals is that they are more electronegative. And why do you think that is? Why are non-metals generally trying to pull the electrons towards themselves? Towards them?
Maybe less amount to fill up to be more stable.
They need less than what?
The metals, because metals are on this side.
Yeah. So how? What are the metals thinking to gain stability? Are they trying to get electrons? I will get. They are trying to lose electrons, and the non-metals are trying to gain. Yes, Joseph.
Yeah, I was going to say that.
Yeah. So it makes sense that non-metals generally have an electron gaining tendency, and we are putting. And people have put numbers on it too, electronegativity, like the actual numbers, but we'll not go into the numbers as of yet. So F generally seems like it's going to pull the electrons towards itself. So this thing, whenever you have this is a bond. This line between H and F signifies a covalent bond, and this shows that an electron is being shared. So one electron is given by H and one electron is given by F. So this basically has two electrons and there is a bond between them. So H now has two electrons. So hydrogen and helium get stabilized because it only needs two electrons in its outermost shell. So it has 1s1, so becomes stable. It just needs to become 1s2. Why will it not do the octet? Because there is no space for the octet. So there's just one box. So it had one electron, it will just try to take another and just fulfill its doublet, if you may. Okay. So H becomes stable because H wants two electrons and it got one shared electron from F and it formed a complete doublet for itself. And F in return also had one electron from H, they're sharing that. And F had 7 electrons in its outermost shell. So F was 2, 7. So it just needed one electron and it shared. It's like they're roommates. Both needed like a table, and one brought 2 legs and the other brought 2 legs, and just stick it together and now both of them are using this table, something like that. Okay, it's like a shared space. The moment they want to get out with it, they can. Now, this thing is called bond fission. Okay, so this can happen, bond fission. Now, 2 types of bond fissions can happen, and we'll look into that. Let's look into another example. So HF, HCl, all these will be similar. Let's see in an example in which 2 electrons are being. Okay, in this case, F has more tendency to grab that electron, right? So generally, if you see an electron cloud, that electron cloud will be something like this. And H gets a smaller share of that, and F tries to pull in that electron. towards itself. And this behavior is called electronegativity. So F, being more electronegative, is pulling those electrons. Now, what do you think the electronegativity is going to do from left to right? It is going to increase, and from top to bottom, it is going to decrease, right? It's very simple. Okay? Now, electronegativity of noble gases. What do you think the electronegativity of the noble gases will be like? Are non-existent. Why? Because they don't pair up. So if they don't pair up, because of their complete octet, or in case of helium, the doublet, there is no pairing, so there is no electron affinity, basically speaking, because electron affinity is basically defined when you have a shared pair. Okay? Now, take a guess for the most electronegative element in the periodic table. It has to be on the right, on top. Chlorine or fluorine?
One of the two.
So it has to be one of the halogens because they are on the right hand side, and the top is fluorine. So fluorine is the element which has the maximum electron affinity, followed by chlorine, blah blah. So fluorine is the one with max electron negativity. Electron affinity, which was the amount of energy released when an electron in its outermost shell accepts an electron to form an anion, also has a similar trend. It increases from left to right, decreases from top to bottom. So fluorine is the most electronegative. Which element has the maximum electron affinity? Think about the halogens. So electron affinity increasing from left to right. So you'll have them. It has to be in the halogens. Now my question is, which halogen? Let's just focus on the halogens. FClBrI. So for FClBrI, the electron affinity decreases from top to bottom from F, Cl, Br, and I. So fluorine, right? But it's not. Chlorine has the most electron affinity. And why do you think that might be? Nature doesn't have to follow our rules. Nature doesn't have to follow our rules. It just follows its own rules. And for some rule unknown to us, nature doesn't know that we formulated these rules. For some unknown rule, which makes sense to nature, it might not to us, chlorine has more electron affinity than fluorine. And why do you think that is? Think about what electron affinity is, and what would happen when you're basically trying to push in an electron, right, into fluorine and into chlorine. So whenever you have to decide between what is happening, you just think about a reaction and see which is the more stable product, okay? So basically, it's something like this. Which of these products will be more stable? Why? Because I said the answer.
Well, I don't know, because isn't like fluorine like really unstable?
Why? It is. And that's why you hear stories about fluorine all the time.
Yeah, it's just It's unstable.
And why is that?
Does it have to do with its electron configuration?
Electronic configuration is more or less the same it's like 7 in the outermost.
Because of the state that it's in, like in nature or something? That's something to do with that.
Because of the size. Think about the size of fluorine. What general idea do you get about fluorine? Is it big, small? It is very small. So its size is decreasing, and size is decreasing when you go up. So basically you have very small sizes in here, towards this right side on the top. And because of the small size, you're trying to push in one more electron, and it's already small size, it gets too crowded. And that is why this becomes very unstable, F minus. And since it becomes so unstable, although it has great electronegativity, it wants minus, you want something so bad, but you don't have the space to keep it. You're like too crowded, you have too crammed up, and that's why you are unstable. You want it, but you're too small to hold on to it. And that is why it's making it so unstable. And that is why chlorine's electron affinity is more than that of fluorine. Because F minus is less stable than Cl minus. Okay? So whenever it comes to fluorine, and you think about its small size, it behaves weirdly because of its small size. Fluorine, chlorine, like these are really special, really high electronegativity, small in size generally. So it wants electrons, but if you cannot keep it, it's a problem. Okay? Now, you have maximum electronegativity. Now, what if you have Cl2? Let's see the case for Cl2. So both of them have 7 electrons in its outermost shell, and both of these needs 8 electrons to fulfill its orbital. What will they do? Will one give its electron to the other? No, because they're equally electronegative. They're not going to share. No one wants to lose an electron. It's their equal. So the only way they both become stable is to share these electrons. Okay? So we show this sharing by a bond like this. And we know that now this chlorine has access to 8, and this chlorine has access to 8 electrons. For oxygen, how many electrons are there in the outermost? 6. So how many will they need to share? 2. So we put 2 in the middle. 6 electrons. They are going to pair up. So basically you're forming O double bond O, because there are 2 bonds that are forming. But what will happen for nitrogen? How many bonds? 3 bonds. Because there are 3, because it's 5 electrons in the outermost shell, needs 8 to fulfill its orbit, 3 bonds. Now, you're forming these bonds. Can anyone guess which of these bonds will be strongest? A single bond, a double bond, or a triple bond? So you have an O double bonded O, Cl double bonded Cl, or you can also take F, so F single bonded F, so you also form F2. So if you want to compare, I'll just so you have to compare between sorry. So I'll give a name to the number of bonds. I'll call them bond order, which is just the number of bonds. Simplicity's sake. So this term, bond order, is being termed in molecular orbital theory. I'm not getting into that, but I will give you enough information so that you can use molecular orbital theory to understand chemistry. So bond order is just the number of bonds. So what's the bond order for F2?
Single bond.
1. So it's 1, 2, and 3. Okay, so bond order is fine. Now, which bond do you think will be the strongest?
Triple.
The triple one will be the strongest. Because there are 3 bonds that are being, so there are 2 people in a relationship and they're sharing more things between them. Which bond is strongest? Like the person who's sharing the most amount of things versus a person who are not sharing those many things, right? So the element who is sharing 3 pairs of electrons has a stronger bond, and the bond order, therefore, is proportional to the bond strength. So the one that has more bond order will have more bond strength. Think what will happen to the bond length. So there are 3 things: bond order, bond strength, and bond length. So the length of the bond. Which do you think will have the longest bond?
Fluorine,
Why?
because it's not the strongest either, so it needs more room.
Yes. So a longer stick breaks more easily than a shorter stick. So this is like, I broke it. But if I take like this, I probably won't be able to break it. Right? I'm actually trying. So that's the thing. So which of these 3 do you think is the strongest? N2, and the shortest is N2. So there is a relationship between bond length, bond order, and bond strength. And the interesting thing that comes from molecular orbital theory is that isoelectronic species will have same bond order. Should write this down. So isoelectronic species have the same bond order.